Today we're starting exponential functions. We got exponential growth. We got exponential decay. I'd love for you to be able to write and evaluate exponential expressions to model growth and decay. And of course, you'll be great at it because you're all very smart. So an exponential function will be like y equals some number, some base to the x. The x will actually be the exponent on this. So your graphs are going to look, they're going to be either curves upward like that, or they're going to. Now, can you guess which one is growth? Yeah, the one that goes up. So this would show exponential growth, and then the one that's dropping would show your exponential decay. That was actually a bad drawing for the exponential decay. It actually looks more like this. So it starts high and then comes down low. Now you'll also see this word asymptote, which is an imaginary line that this graph will never touch. So for exponential growth, it might look like that, and it might be like y equals 0 or something. Not the most important thing. It'll get incredibly close, infinitely closer to that line, but it'll never touch it. So that's the asymptote. Let's see, what else we got here before we actually get into it. We got it. So here we go. Tell whether the function shows growth or decay, and then graph. Now the graphs are not the most important thing. You could just type them into desmos.com and it'll graph it for you. But here's the deal. You're going to look at the thing with the exponent, the base, as like a starting point of 100%. So it'll be base to the x, right? Y equals base to the x. Now if we're starting to think of that as like 100%, which is 1, right, as a decimal. If it's anything greater than 1, the number with the exponent, it's going to show exponential growth. Now, if that number is lower than 100% or less than 1, that's going to show exponential decay. So it has to be between 0 and 1 for decay, and it has to be greater than 1 for growth. So if you look at the number with the exponent here, we have 1.5. That's larger than 1, so that would show growth. Now, if it said what was the growth factor, then you could just subtract 100% from it. So 1.5 is like 150%. If you subtract 100% off of that, its growth factor is 50%. They're not even asking you that here, but you're so smart, I knew that wouldn't even be a problem. So now check out the graph here for f of x or y equals 1.5 to the x power. So you'll see this is the asymptote, the y-axis here. It'll never touch it, even though it looks like it does. But then it just starts to shoot up quickly after you get past the y-axis here. So if you put in 0, right, anything to the 0 power is 1, so that's why it crosses here at 1, and then it just skyrockets after that. So let's check out the second one. G of x equals 30 times 0.8 to the x. Now again, we are looking at the thing with the exponent, that base. 0.8 is like 80%. That's smaller than 100%. So that would show a decay. Now, if I said, what's the decay factor? If you did 100% minus the 80%, that would be a 20% decay factor. Pretty sweet, right? So always start thinking of it as 100%. So here's what the graph would look like. Starts off nice and high. It's the y-axis at 20, and then it just drops. And you see it gets very, very close to that x-axis, but it'll never touch it. So if you look at this last one, this is the one I was going to have you try. Tell whether the function p of x equals 5 times 1.2 to the x shows growth or decay, then graph. Here's the graph for it, which obviously shows growth because it's shooting way up there. But if I said what was the growth factor, if you look, 1.2 is like 120%. If we subtract 100% off of that, we're left with 20% growth. Now again, it's not even asking us that yet. It's going to, but I knew you guys are so smart that it shouldn't even be a problem. You've got this.